Hello again. Tonight we're going to talk about black dwarf stars. You might not have ever heard of them, but you've heard of a counterpart of them. So once again, I'm going to be doing a little postulating here. You've probably heard of white dwarf stars, but may not have heard of black dwarf stars. Think of a white dwarf star as being a star like our sun at the end of its life. It's not big enough to go supernova. It just shrinks down into a white dwarf, a little burning ember of itself, high density, same gravity it originally had, but very small size, usually about the size of a little bigger than the Earth, down to as small as the Moon or a little less. But they typically radiate, as a white dwarf would indicate, in all sorts of spectra. But what happens when they get cooler? I mean, they've run out of their nuclear fuel. They're going to get cooler and cooler over long periods of time. And it turns out they have a classification for what you call a white dwarf when it's cooled down to the point where it's no longer visible in infrared or visible light. Therefore, it's not detectable. Therefore, it's black. White dwarfs become black dwarfs. And I'll postulate exactly why we can no longer observe them and how we might be able to observe them once again. So this is our NASA Night Sky Network poster of Life of Stars. And you can see at the just left of center at the top, a sun-like star. It'll become a red giant and then make a planetary nebula and then become a white dwarf. And that's the ultimate fate of our sun. Over on the right side, you've got the bigger stars like Betelgeuse, become a red supergiant and go supernova, eventually turning into either a neutron star or a black hole. So we're only going to be talking about the ones that go white dwarf. So we know of a number of white dwarfs out there. They've burned up all their primary fuel, their hydrogen, helium, and all the way down to iron. That's when they collapse. They'll blow off a shell of material, forming a planetary nebula, and then the stellar remnant will shrink down and form a white dwarf. And the nearest one that we know about that we have pictures of is there on the right. The big bright one, that's Sirius, Canis Majoris Sirius. The little white dot below it, that's actually Sirius B. Sirius B is a white dwarf in the same star system as Sirius. So it's a little white dwarf. They don't explode, don't go into nova, supernova, or hypernova. They don't degenerate down into neutron stars or pulsars. They don't collapse into black holes. Initially, when they shrink down to a white dwarf, they are hotter than the sun, but absent their elemental fuel for fusion, they cool down in a non-linear fashion. So they'll start off hot, and then they'll get to a certain point, and then they'll go kind of roller coaster down to a plateau. And if that plateau falls below a certain level, then we'll no longer see them as white. We'll start to see them as red or infrared or other wavelengths, but eventually when they go down far enough, and right now it's theorized by others, not by me, that this may take many billions of years, some even say trillions of years. So we won't be able to see this for the remainder of our existence around our star. Okay, that's they know the chemistry for what's going on there, but they've never witnessed it. So I'll just say, if a white dwarf existed for billions of years before early 1900s, when we started observing in infrared, how would we know how long it's been cooling down and when it's going to shift from infrared into invisible? We didn't start observing until after a lot of them were already cooling down. So how we'll know exactly when they're going to shift down, we don't know. So if you think of a white dwarf that's part of a binary star system, at the end of its life, when its partner went nova, that binary white dwarf actually got ejected from its star system and therefore is got a rapid velocity along a particular angle. They would categorize that as a rogue white dwarf star, because it's no longer part of its original stellar system. Preferably, it's not heading towards the Earth in our solar system, but I talked about that in earlier for our astronomy presentation. Even though an angular velocity might be high, a good portion or a non-trivial portion of the speed of light. But across the sky, that's only tiny fractions of an arc second of a degree over maybe a decade. Now, wide field stellar observatory imagery is not going to have them moving by much, and they know how to take care of that in the wide field. So once a white dwarf cools down, and it cools down to the point where it's no longer even radiating at the infrared level, it becomes one of these theoretical black dwarf stellar remnants. Now, I didn't come up with the concept of a black dwarf star, a black dwarf stellar remnant. I just went out there and got the information and pulling it together. The realization is that they should still be there. So, when it became a black dwarf instead of a white dwarf, it didn't go away. We just can't detect it anymore. It's still there. It still has considerable mass. Emissions may not be visible in infrared, but there are other wavelengths we can look at. We need to find these things and put them in catalogs so we can watch their cooling progression. But maybe we're just looking at the wrong wavelengths. We should stop looking for them in visible or infrared and start looking for them in other wavelengths like radio. Radio extends up into the very small micron level wavelengths or terahertz wavelengths. So we should start looking for them at that level. The problem is that terahertz wavelengths don't easily pass through the Earth's atmosphere. So they may go from a white dwarf to a red dwarf to an infrared dwarf to all of a sudden invisible because the Earth's atmosphere is stopping their initial radio propagation. So we need to, how do we look at this? Well, we do have Earth-based microwave radio astronomy observing centers, the Very Large Array, and then the Atacama Array in South America. So maybe that's how we should start looking for them. So this is the Very Large Array, another one of those catchy terms for describing something. What should we call it? What is it? Well, it's a very large array of radio telescopes. Good name, VLA, we got it. It's actually called the Jansky Radio Telescope, named after Carl Jansky. When you look at the units of radio energy, things sending emanations to us, it's measured in Janskys. It's not something made up in science fiction movies. It's actually a unit of measure of radiant flux in radio. It's at 6,970 feet, which you would think of, that's pretty high, but it's not all that high because it still snows there. So there is still moisture left in the atmosphere that is blocking certain radio frequencies. So I broke it down and said, well, all they told me was they can receive from 1 to 50 gigahertz. So I had to convert the frequency to wavelength in meters, and then convert the wavelength in meters to millimeters or microns or nanometers, so I could compare it with light waves and infrared. And suffice it to say that 1 to 50 gigahertz is not really great for trying to look at something that has just gone from infrared to the shortest possible radio wavelengths. But it's a start, so they could start looking for them. What about ALMA down in South America, the Atacama Large Millimeter/Submillimeter Array? Yeah, it's very high. It's at 16,597 feet. If you're going to be working outside on the radio telescopes, you have to actually have a little bottle of oxygen with you. You always have an oxygen mask on because you're above 15,000 feet and the air is very thin. But notice the drone picture below. There's snow on the ground. That means there's still water vapor in the air above it. You can go high, but only so high. I don't think we're going to put radio telescopes on the top of Mount Kilimanjaro or someplace. But it's a large number of radio telescopes, and they're a variable interferometer. There's some ability to move them, but not as much as the VLA. The VLA has railroad tracks everywhere, and this just has a giant tank that can lift up the telescope and move it if it has to, but they typically don't move them. So I looked at its frequencies. It'll go up to 950 gigahertz, which is not quite a terahertz. Terahertz is the next up from gigahertz. So if you had 1,000 gigahertz, that would be 1 terahertz. Infrared light is even up higher than that. So we have a gap, and that gap is because it's blocked by water vapor in the sky. But what about once they cool down even further and they're sending out radio waves at potentially even longer wavelengths? Well, that's when you need a lot of radio dishes. Now, this is an artist rendering. We don't actually have this yet. We have maybe 30 or so dishes. We don't have this large array that you see here, but this is the square kilometer. You can tell it isn't from the US because they spell kilometer. The square kilometer array. Well, they've built a few of these, so they have the dish design down, and they've got operationally a few of them working. But they want to build an enormous number of these, spread kind of like randomly, like a shotgun blast, around a very large flat plateau. These are much lower frequency, much longer wavelength, so we'd have to wait until the black dwarf stellar remnant cools down even further. But the other thing to think about is the actual resolution, like kind of like the pixel size of this radio telescope array, is not meant to find small, nearly black things. It's meant to find large structures in the universe, like galaxies or globular clusters or nebulas or filaments. I would still say Atacama is probably our best bet at this point. But remember, at one point in time, that black dwarf was a white dwarf. And before it became a white dwarf, it was a star like our sun that had maybe planets around it and comets and asteroids orbiting it. The junk you normally have in a solar system. If the planets weren't destroyed when it went red and then became a planetary nebula, so long as life on the planets weren't cooked when the white dwarf was emitting X-rays, a black dwarf is likely to still have planets orbiting it. They may be decimated planets, but things still orbiting it. The outermost planets from it, if much like Jupiter and Saturn, had giant moons that had maybe oceans on them, maybe these were habitable, because these things don't happen overnight. You can see, like when your star starts to puff up to be red, you've got maybe 1 million years before it will become a white dwarf. So you've got time to move out of that neighborhood to the farther out, move to the suburbs. If life was in one of these solar systems that had a white dwarf and they moved out to the suburbs, that life could have existed for several billion years longer than life has existed on planet Earth. So their technology could be very advanced. Now, the neat thing about how we would spot these planets, if you've looked at how we find exoplanets through optical observing, we put a giant disk or some shutters in front of the bright star so we can see the much dimmer planet being reflected by that star. This would be much easier because that star has already become a black dwarf, which means it's not radiating in white light or infrared, it's dark, and therefore the planets would still be visible. You just have to know where the black dwarf is located in order to target your optical instruments to look for localized radiation coming off of those in the visible spectrum. They're so far away, so small and so dim that without knowing where the black dwarf is as a center of observing, you're never going to find them. So we look in radio. This is a chart of the various wavelengths of radio. You can see wavelength along the bottom in angstroms. We always got to have different units. Why we can't just scale up like nanometers? Now, angstroms, microns, can't just keep everything metric. And then on the left side, you have obstruction. If you see the graph going way up, that's basically your ability to see through it. So you can see there on the left where it says optical. 1 means you can see 100% of the optical wavelengths coming in at that particular frequency range. And you can see there's an I, J, H, K, L, and M. We'll get to those as we talk about cataloging. These are the different colors or wavelengths of light coming off of stars. So if you go to a catalog and then you look at all the luminances or all the brightnesses, you'll see these letters next to them, what wavelength that light is, how bright. So what we want to do is use ALMA for the wavelengths that it can see through the atmosphere on, and hopefully we can see down to a resolution of a sub-arc second to spot something as small as a black dwarf. But that's going to have to be on specific wavelengths. So this is kind of where it started to be curious, that I found that there is a thing known as white dwarf stellar remnants disappearing. So we're doing these surveys all the time from various observatories, various spacecraft, very broad surveys looking for all the little bright points of light in the sky, usually in infrared. And they get cataloged. The U.S. Naval Observatory, or USNO, has maintained catalogs of stars, galaxies. They catalog when new things come in, like when a star suddenly turns on. They catalog when things disappear. They'll change the catalog or update it if something that disappeared comes back because some debris passed in front of it, something else closer passed in front of it. That day they had a cloud, so they couldn't observe it, or just something went wonky with the instrument and we didn't have a good shot for that time. So they monitor, they create these large historical multiple revision catalogs to try and keep track of all this stuff. That, and they keep track of the angular velocity of the stars. So over decades, as the stars are moving across the sky in various directions, they track them all. So I found that there is a long-standing program called VASCO, or the Vanishing and Appearing Stuff During a Century of Observations. Now, if you remember back when we used to do film observing, they would have photographic plates on glass, not color, black and white or grayscale. And there has been an effort to digitize all of those plates so they could be put into the U.S. Naval Observatory's catalog. So they know historically from the early 1900s, many billions of stars in our galaxy. Observing session over observing session, they'll see stars that they saw, they knew where they were, they moved a little bit. Okay, plot the velocity curve, and they watch the velocity change and the position change. Or there was not a star there, all of a sudden there is a star there. They see a star turn on. A star was there, it didn't move because we would see it in the area, it went away. And then later on it came back. Well, some debris might have come in front of it or get blocked or whatever. So it comes back. But those are, okay. What about the ones that they know there was a star there, the star's been there for a long time, and all of a sudden the star is just not there anymore. It didn't explode. I mean, it's already at the end of life, so it's not going to go nova. So they think that this is a sign of extraterrestrial intelligence, like they build a Dyson sphere around their planet or something, and you can't see the light anymore. They're hiding from us. Like, I postulate it's maybe something different. You're only looking in infrared, and it's cooled down sufficiently to go over that knee in the curve to say, I can't see it in infrared anymore, because all of these wide surveys like Gaia, Sloan Digital Sky Survey, Pan-STARRS, they're all looking in infrared. And with the exception of Gaia, they're all looking from the Earth's surface. So you've got the moisture in the atmosphere that says, you're going to do infrared, but only the near infrared. You're not going to do the mid to deep or deeper than infrared. And even Gaia only gets to the mid infrared, doesn't get to the deep infrared. If the light that's being emitted falls below the threshold of your sensor, I don't know what happened. It suddenly just disappeared. It went black. Nope. It just, if you can only hear in a certain frequency range and somebody starts talking in a frequency range below what you can hear, you won't hear them. So in order to transition this from my postulation to mainstream, we need some data mining. I'm not going to do this other than what I've done for this presentation because, as the saying goes, my plate is already quite full. But I think if somebody looks at this presentation and they have access to this data, which may not all be public data if you're looking for the raw information, might be something to look for. It's just an algorithm. You can let the AI stuff go run over gigabytes of data, for months at a time and see if it pops up anything. So I'm not looking for the thing that was, there in some versions, not there in others, but it's still there. Ignore that. Some have gone away but then returned. Ignore that. How about the things that were there for a long period of time, went away, never returned, and there was no nova? That's the ones we're looking for. They can track over time stars as they go from active to white dwarf to a reddening white dwarf to gone and never returned, likely no longer emitting an infrared that can be detected. So here's where those letters come in. When you're going and looking for, well, what kind of electromagnetic radiation or light is it spitting out? Well, when it first becomes a star, you might get some gamma. And then as it gets towards the end of its life, it'll be higher energy. So it'll start putting out X-ray and ultraviolet. And then as it becomes a white dwarf, it'll put out less ultraviolet and start shifting down into towards the red and the visual or white areas. And they actually classify what would be thought of as film photographic magnitudes as PG or L or Z. So there's all these letters that when you see the columns of data, it's like, what is a Z? That's your basic luminance, just basic brightness across the spectrum. But there's infrared. There is a letter for near infrared called I, but there are no letters for mid or far infrared because there aren't any things on the Earth that can observe in mid and far infrared. Then you'll have specialized ones. You're like H for the hydrogen line. And you've got I don't know who Johnson was, but the Johnson specified infrared lines, which are J and K. I couldn't find details on them, but I'm sure that it's probably some guy named Johnson a long time ago created filters who have a center line of this J and K. And then, of course, you have radio, which are named by the band, the wavelength, the frequency, and then the bandwidth of the signal. You might think it would be an easy thing to just go, well, just tell me what the stellar magnitude is. They use different algorithms for measuring that based upon the instruments that are measuring it. How about just tell me what the flux is, the photometric flux? That's, a physicsy thing. Well, even that has different definitions. You have one that's, if you pick a particular point in time and say, how bright is that? And you say, how big your sensor is. Then you can convert the photons to electrons to volts based upon the chemistry to watts, the size of your sensor to be watts per meter squared. That's a number. But all those things that get cataloged by observatories don't measure flux using that numbering system. The closest they might get is luminosity, which adds a time, which says, how bright is it over that square area over a period of time? And they don't measure watts, they measure joules. So joules per meter squared per second. So it's all over the place. So you have to map it. So if you see a set of observations, you have to map those to some common value so you can judge apples to apples instead of trying to compare apples to kumquats. And then if you use just astronomical magnitudes, realize that that takes brightness and throws in distance to target to come up with a magnitude number. Now it's just a simple numbering compare. But it's doable. There are means of mapping this to that to come up with what you need. The particular characteristics of a reading, an observation, are also based upon what kind of sensor technology you're using, what kind of filters are you using, what's their center wavelength, their peak, signal technology. So you have to find out what the curve looks like. And if you look at the SIMBAD catalog, they actually have all of these things recognized because they know that the red for SIMBAD is different than the red for SDSS, which is different than the red for Gaia. So they'll give you different letters for all that stuff, and it's up to you, the observer, to map all that stuff. So as Helen pointed out to me last week, there is a place called Kaggle. This is a website that has cloud-based storage and cloud-based computing algorithms and such. They do have a lot of infrared data sets and different versions of them, and it's freely available for you to go use these sources. So I have an account on Kaggle, so I could do this, but what I found out was their data sets were modified. So if I'm a principal scientist on a program and I need the SDSS data set, but I'm only looking for certain things like galaxies, then I may take a particular version of the SDSS data set, throw away all the stars, filter all the galaxies that are within a certain distance, and that's what I'll call my contributed data set. So I'll contribute freely that data set to Kaggle. Well, that data set would be useless to me. I need to get the raw data set so I too can filter it down. So I wouldn't think of the data sets available in Kaggle, I'd go back to the source and get those. But Kaggle is a good place that if you know Python, you can take the data set and do your own filtering algorithms in Python, and you can actually contribute those filter algorithms to other people creating other reports on Kaggle. So it's definitely a collaborative environment. But not for me. There's too much normalizing work that I'd have to go through. I'd go get the original source data, renormalize it, publish the algorithms on Kaggle. I'd rather just quickly do something. As I say, I'm busy frying other fish. It wasn't so busy frying other fish that I couldn't at least list, if somebody is interested, this is what it would take to take the raw data sets and versions of them and then wade through that with data mining to find what we're looking for, which is black dwarf stars. So across many billions of stars, maybe half a dozen data sets and maybe half a dozen different versions of those data sets. And then, dealing with all the differences in electronic sensors and filters and some archived historical photographic plate data, taking into account stellar drift and angular velocity. This is what you would have to do. The data sets, in order to make them small for internet download, they're all compressed. So you need to uncompress them. But they all call the files the same name. So you have to put them in separate folders. Otherwise, when you uncompress, you'll overwrite the previous version. That at least include the date and the file name. Then you have to separate out the meaningful data values from the irrelevant stuff. So you might find that in the compressed data set, there's 5 files. Only one of them is actually the data. The other is telling you how the table is set up, or a user guide to it, or whatever, or updates in this release. So throw those files away. Change the file names so that they're consistent, so you can write an algorithm that goes across all of them. And the files can be at different formats. You can have your typical comma-separated value, which is easy to get into Excel. That's for SDSS and some of the Gaia databases. But for other Gaia, they wanted to be real astronomy, sciencey about it, and they put them in FITS format. So you have to go get something that will uncompress the data, convert the FITS to CSV, and label it so it can be imported into something like Excel. Just more work to do. Not impossible, just it's hard work. Not impossible, just hard work. If you look at the SDSS and the Gaia object IDs, because every one of these stars has to have an identifier, and the identifier can't be Sirius. It's got to be some gigantic J started 2 mass number that tells you basically the coordinates of where you spotted it at. But given they're in different places, some are on the ground, some are in orbit at L2, the angle that they look at is maybe going to be a little off. So for the same star, the SDSS and Gaia object IDs may not be exactly the same number. They may be a little different. So you have to map those. You then have to take into account the sensor luminance. And Gaia likes to show you things in mean magnitudes with accuracy indications, whereas SDSS actually gives you the channel luminance values. Then the names in the tables are all over the place. If you go to SDSS, OBJID in one version can be OBJ underscore capital I capital D in another version of the same data set. So you have to deal with that kind of stuff. Positioning, SDSS calls it RA or alpha. Gaia refers to it as RAJ2000. So you have to adjust all this stuff. In SDSS, to kick out the galaxies, they actually have a class column in the table. So you can go in and say, okay, take all the things that are galaxies and are quasi-stellar objects like filaments and debris, and just don't care about those. And there's a column called redshift. Redshift actually tells you if it's negative, that star is moving towards us, as opposed to positive redshift, which means it's moving away from us. You have to sort of figure out all that stuff. So generically, here's my black dwarf stellar remnant candidate algorithm. So once you've normalized all the data, if a star has been in any version of a data set, that's what you want to look at. If it's never been in a data set version and it suddenly pops in, okay, that's fine, as long as the quality of the observation in all the various channels is not indicated as minus 9999, which says bad sensor data, like something went wrong and we didn't get a good reading. So you'll ignore that observation, but keep registered the fact that you've got to start at that location because a future version may show it. So if the star was there, went away, and then later on came back, ignore that one because it's still there. So if the star was there, went away, and never returned to any of the previous classifications, and the previous classifications across all the data sets said, hey, this thing is getting redder, dimmer in infrared, and then all of a sudden we couldn't see it anymore. That is a black dwarf stellar remnant candidate. When you find one, look over across to the astronomy, the radio astronomy data sets, and see if something shows up there. That's how you see it transition from white dwarf to black dwarf. For those people that aren't familiar with Excel, but are familiar with like writing things in Python or Java, JavaScript, or C or C++, they may not realize that the current version of Microsoft Excel is pretty capable at data analysis. I did actually pull in some files into Excel, which can now support over 1 million rows in a table. You can create additional columns. You can filter out the bad stuff. You can flag when you have duplicates. You can freeze the row at the top. So as you're scrolling up and down, you can always see the columns. But if you really want to do some algorithms on it, there's Microsoft Visual Basic for Applications, or VBA. And besides that, Excel will run far faster in data analysis than will some algorithm running on a cloud server. So I ran the data through Excel. I looked at SDSS datasets versions 12, 14, 16, and 17, because those are the ones I could find raw data on. And I actually found a candidate. So the way I found the candidate was I was looking for something that disappeared, that basically was there on version 12 and then suddenly dimmed down in infrared and then was no longer there. One candidate out of the 127,000 white dwarfs that I looked at, something to look at. So then I went through and just hand scanned for the trend of R and I dipping down and the luminance also declining. And I found this one. This one's actually too dim to be seen in stellarium or in starry night. But is this an indication of one that's cooling down and about to disappear? Well, I don't know. You'd have to actually look at it over time. But if you do find one like this, I'd say start looking at it at the highest possible radio frequency your receivers have and see if you can see it. And you can actually start with a white dwarf, look it up in Simbad, switch over to VisiR, which will show it to you in infrared, and then you can switch over to what is known as SED, S-E-D, to find a graph of its radio emissions. So you can say, I saw this white dwarf, and then later on I saw it as more infrared than white, and then later on the infrared started to decline, and jump over to SED and see if you can find a graph of it's already being looked at in radio. So breadcrumbs. But in order to see these better, we're going to need a long wavelength radio telescope in space, or an array of them in space. And I came across a U.S. Naval Office of Reconnaissance, an NRO satellite. It's a spy satellite, basically. And if I said, if I could turn this antenna from being facing down to the Earth to facing out into space, and if I could still talk to the satellite, when this thing goes obsolete or gets superseded by newer technology, that would be a candidate. And earlier this evening, I actually sent an email off to the Public Affairs Office of the U.S. National Reconnaissance Office, the folks that run the spy satellites, they work with the NSA and the CIA and such. It turns out, as newer technologies come along or they make better satellites, they retire the old ones. And I basically asked them in an email, hey, when you retire the old ones, if they're declassified, what about pointing them out to space and using them for radio astronomy to be able to pick up signals that we can't pick up through the atmosphere of the Earth, or signals that are in conflict with the bands that are not allocated for radio astronomy. So regular radio bands that people have used for computer and voice and Morse code telephony. And we'll see what they say. But the idea would be, if we could get a satellite to start doing this, that would be, hey, look what we found. If we could get a satellite to be commissioned, by NASA to be put up at L2 just for radio astronomy in these very high frequencies, that would be another way of looking at things. Once we find a black dwarf, then we can task, the other more popular observatories out there to look at them in visible and UV for planets that might be orbiting that black dwarf. So let's say we suddenly find a way to look for black dwarfs that's successful, and we say, hey, we know how many white dwarfs are out there. If there's that many white dwarfs over the many billions of years of existence of the universe, maybe there's a lot of black dwarfs, and we start finding lots and lots of black dwarfs. If we find them, that's a lot of mass. The mass of the black dwarfs plus the mass of their Jovian planets. Should we go back and reevaluate, how old the universe is based upon the purported, well, it doesn't become a black dwarf until it's, hundreds of billions of years old. If we find lots of black dwarfs, maybe that number's not right. But what if we say, the number's okay? Well, what about all that mass? We suddenly found a lot of mass that was dark before or black before. Should we go back and recalculate things like the mass of a galaxy? Because we suddenly find, let's say, 500,000 black dwarf stars in our galaxy? That's a lot of mass. Could that make other things that we think of as dark not be needed? And if we do find that there are planets orbiting black dwarfs, and we do find either visible, infrared, or radio signals coming from them, if there's something alive on those worlds orbiting black dwarfs or moons orbiting Jovian planets orbiting black dwarfs, then they will have had billions of years of time, should they have survived, to advance well beyond where we are today. And in conclusion, white dwarfs exist. We have all sorts of records of those. Black dwarfs as stellar remnants are still theoretical because we haven't spotted any yet. But we need to start looking for them in other than for infrared, because if they cool down to the point where we can't see them in infrared, we can't see them. They go black on us. We need to start looking for them in the highest frequency radio wavelengths, shortest possible radio wavelengths, and then lower. We need to data mine the data that's out there for white dwarfs to see if we can see them transitioning to becoming black dwarfs. Once we realize a way to detect them, we'll probably find them in large numbers. So let's stop looking in infrared for them, start looking in, terahertz radio to see if we can find them, and then look for planets around them. If we do find planets, there seems to be signals of life on those planets, then they've got a few billion years head start on us. Once again, all about me. I did lots of research, so you'll find lots of hyperlinks, a couple of pages of them.
You always do lots of research.
This one took me almost 2 weeks to put together.
Yeah.
Well, I did spend some time with Excel and with Kaggle and things like that. Okay, prior to tonight, had anyone ever heard of a black dwarf star? But they've been postulated for a long time, but they were only theoretical. And it's one of those things like, we're going to talk about string theory in mathematics because you'll never be able to see the 10 or 11 dimensions in the real world. So give us more money to not see something we told you couldn't see. Well, this is slightly different. If the reason why they become black dwarfs is because they cool down and they're no longer radiated infrared, they're probably radiating in very high frequency radio, which your infrared detector can't detect. So give somebody some money to go detect them in very high frequency radio using satellites, even orbiting very high above the Earth initially. L2 would be nice, but at least what they call super synchronous orbit. That's higher than geosynchronous. It's kind of like geosynchronous, but even higher. Those are orbits that can last many hundreds of years. So, any comments or questions?
Technical about radio astronomy arrays,
Yes.
antenna arrays. They function as one large antenna.
There's two approaches to doing that. What they are doing is something known as they're creating a synthetic aperture. And the way you do that is you slice up all the data and you determine the location and the timing down to, fractions of a nanosecond, if possible, of all of the electromagnetic radiation being received. So now you know how to create basically a giant parabolic, synthetic, or virtual receiving antenna over that large array. And you can either connect all the radio telescopes together with a fiber optic link and synchronize all the data down to a sub-nanosecond level. Or you can have a very accurate atomic clock associated with each receiver and timestamp all the data. And then you take all those petabytes of data, take all the solid state drives out of the array receivers, put them on pallets, and ship them all off to the VLA in New Mexico. And they have supercomputers that will process all of that array data into synthetic aperture observations. The antennas don't have to be close together. In fact, if you get the antennas too close together for the accuracy of your timing, you get what is known as aliased signals. So you can't tell that this antenna is different than this antenna because they're so close together, they might as well be one antenna. So you want the antennas to have a certain minimum distance between them to avoid having to deal with anti-aliasing. But you can take that out further and say, well, if I give up on the amplitude and I have the selectivity over that wide band, I can make a synthetic aperture radio astronomy antenna farm into a single receiver that might be thousands of miles across, or might actually extend from Hawaii to the US to Europe as one giant Earth-sized antenna. And that's called very long baseline interferometry, VLBI. And there's a special kind of that called Earth VLBI, or Earth diameter VLBI. So if I want to point all in one direction when I'm observing, I can't use antennas over the curvature of the Earth because they can't, they'd be down into the weeds of the horizon at best. So you have to narrow it down to kind of a sweet spot of the curvature of the Earth, and that extends from Hawaii through the US over to certain parts of Europe. That's how you take all those individual antennas, gather all the data, accurately timestamp it, put them on pallets, send them off to the VLA, and they'll munge through it on the supercomputers, and then you'll get data out of it. And you can take that data as points and then make an image from it. So you can actually do synthetic aperture radio imaging, where you'll false color the various frequencies as different colors to make high resolution color images from radio data. And
I understand this idea of time stamping, going from one to the other to the other to the other. And then
if you have an atomic clock and you synchronize it properly, you can get out to 10 to the minus 13th seconds very easily. But you do have to take into account weird stuff. Like they did this with an array, and they found out that the orbit of Jupiter around the sun affects the position of the sun, which affects the position of the solar system in the galaxy. The mass of Jupiter, like swinging around the outside of the sun, pulls the sun off center. And so when Jupiter is on one side of the sun, the actual gravitational center of the solar system is not in the center of the sun. It's actually just outside the radius of the sun because of the mass of Jupiter. So when you're trying to do these very accurate measurements, there's a lot of noise that you have to take into account. Who knew? So, any other questions?
I have a question.
Go ahead.
You said an atomic clock, like if you
Yes.
could get it on Amazon. Can you get an atomic clock on Amazon?
I don't know where the Amazon came in, but
No, you just said it like if anybody could get one. You said you just get an atomic clock, and I'm thinking, well, I don't know where I'd get one from.
okay. I can't get down to that level of precision, but I can get down to about 10 to the minus 11th, just with, I buy a particular kind of GPS receiver for my Raspberry Pi computer, and it has what is known as a pulse per second, and that's accurate to 10 nanoseconds. So I can receive that and get that level of accuracy with stuff you can buy on Amazon cheaply. If you want to spend, let's say, close to $1,000 on Amazon, you can buy what is known as a rubidium atomic clock source on Amazon. Those are a bit more expensive, but they don't cost, near what the U.S. National Institutes of Science and Technology, NIST, genuine atomic clocks, that's the ones they use for GPS. It's nowhere near that, but it's far better than what you can get for cheap parts. What they are doing is they have a little oven inside this module that heats rubidium gas to a certain temperature, and then it measures the number of ticks or photons coming off of the rubidium atom. And the repetitive rate of those is very high precision. So that gives you a nice base clock source. But
Now, do I need anything like that? I mean, would I use it for anything?
No, you personally would never need that. For my amateur radio astronomy, when I was looking at doing a synthetic aperture array, I needed the highest accuracy I could get for my dirt cheap radio telescope array. And that's when I discovered using the GPS pulse per second signal. Now, there's special things we have to do with it. Like you want to get the GPS data to not go over a USB interface. You want a raw serial interface working at very high speed. So you get the, once every second to 2 second data as quickly as possible with no lags. But whenever the GPS satellite sends a signal down, it sends a pulse that is perfectly aligned to 10 nanoseconds. The GPS receiver, through a minimum amount of circuitry, takes that pulse edge and produces a parallel pin. That parallel pin becomes a high priority interrupt to your microprocessor chip on your Raspberry Pi at the kernel level, the core of the operating system. And then you take that to line up the 1 second tick within the time of day of your computer. And I could use that to get down to the 10 nanosecond or better level accuracy of my radio astronomy receive signal. So I needed that. I wasn't going to spend money on a rubidium atomic clock. That was just like nonsense. But if what I created, if the software I created, if all the Python stuff and the web stuff that I wrote was good enough, you could map all of that to professional radio astronomy and take it out to like the VLA, or to take it to ALMA down in South America, or to take it out to the square kilometer array. And now you can invite the public to do radio astronomy as an array, because I did all the homework. And then I said, okay, now that I've got all the data and it's accurately timestamped, how do I make images out of that? And the U.S. National Radio Astronomy Observatory, US NRAO, does provide free software, your tax dollars at work, that will munge down this data. That software typically runs on supercomputers out at the VLA, but it's called CASA, C-A-S-A. And I downloaded that. I compiled it and installed it on a Raspberry Pi 4 computer, and I actually got it running, and I gave it a sample set of data, and it took several weeks to just go through like 1 million data points. So I don't have a supercomputer, so I'm not doing that anytime soon. But by me taking my amateur radio astronomy data and reshaping it, getting all the right data points and values to match what CASA thinks of its input data values and definition, now I can create data in my dirt cheap public array that then the big supercomputer CASA stuff could digest. So that was where I was going with it until I just went, this is a lot of work and I'm the only one doing it. So I'll put that on the shelf for a while.
So now would that be stuff you'd be utilizing to study these black dwarf stars that you're talking about?
If I was using a single radio antenna to study it, no. But if I was using multiple antennas to create a synthetic aperture array, yes, I would need high precision timing.
So you're not studying the black dwarf now?
Not right now, but earlier this evening, I did send a letter off to the U.S. National Reconnaissance Office, the people that operate our spy satellites. And I said, so I see that you guys retire these satellites after a while because newer technology comes along. What would be the possibility of when you go to turn down one of those satellites that's been declassified, pointing it up instead of pointing it down, like surveilling different radio signals on the Earth? Point it up. Let's do some radio astronomy with it above the Earth's atmosphere. And we can now listen in on signals that you can't listen to from below on the ground because the atmosphere blocks that particular set of radio frequencies. And we'll see what they say.
So you think there's a possibility? That's why you wrote them the letter.
Yes. Over
Wow.
270 geosynchronous radio capable satellites have been retired in the history of orbiting satellites.
What do you think your response is going to be? You think they're going to think you're a spy?
I've given up on that concept a long time ago. They can think whatever they want to think. If men in dark suits with hats come at my front door, I know how to talk to them. Hey guys, come on in. You're not going to like what you're going to see. How I expect them to respond is, first of all, I sent it to the Office of Public Communication. So I didn't get to any super secret spy guys or program directors. If they don't know what I'm saying and they think I'm just a goofy member of the public, we thank you for your comments. You know, this is going to go on the public record because you sent it to our public office address. In the email, I said, I sent this to you directly to the NRO. NRO. I did not want this, initially for public scrutiny because I didn't want, people poking at it. But I am aware that by sending it to you, it becomes part of the public record, and I'm okay with that. So we'll see what they say. Thank you for your comments. We'll get back to you someday in the future. Bye-bye. Or here's the email address of somebody you can, exchange some comments with. And that might actually be a program manager.
Oh, and then the program manager would have the information so you could utilize the satellite?
No, the program manager would have the information to say whether or not it makes sense to take a retiring, declassified spy satellite, whether it has the ability to point up for the observing antenna and point down for the ground station command and control antenna at the same time. Because remember, they're used to the ground station is down and the things we want to observe are down. So the antennas may not be able to swivel independently of another. Because I want the observing pointing up instead of down, and I want I'm talking to the ground station that's controlling me. I want that one to be pointing down at the same time. Maybe they can't do that. I don't know. But I would need to interact with somebody who understands the programs, understands the technology of what's available, and maybe could find either an existing candidate or a future candidate. We'll see.
So you don't think they're just going to write back and say, oh, yeah, here's one, here's how to get a link to it?
Oh, no. This is the NRO. They are not going to let me have access to it directly. That's just not going to happen. Even if it's been declassified, they don't want some jerk member of the public tweaking their satellite.
So what do you think will come of it? I mean, I thought you wanted to tweet their satellite. That's what I thought
No,
the
I
whole thing
don't.
was about.
No, I don't. What I want to have happen is I want the professional astronomy community. I want NASA. I want the U.S. National Radio Observatory Group. I want them to become interested in this. And I will just act as like the spark that started the fire. Think of it
But
this way.
you're starting a spark so that people will be able to utilize it, right?
Yeah, well, not people, but professional astronomers,
Oh,
radio astronomers.
okay. They don't have to be professional, be a radio astronomer.
No, they don't. But if you want to play with the big toys, you do. Hey, there are professional optical astronomers that are nowhere near the actual telescopes they use because the people operating the telescopes, the mechanical engineers that operate the telescopes, would not let optical astronomers touch the damn telescopes. You are an unknown idiot by comparison, and you will not be touching my multi-billion-dollar telescope. You tell me what you want to observe, when you want to observe it, where it is in the sky, and I'll send you the pictures tomorrow.
Well, that would be nice, wouldn't it?
That's what I'd like. If I can get them going on it, and I say, here's what I think you ought to do, and they watch this presentation after I edit it, if they get going on it and they go, hey, we just found a black dwarf star, first one ever on record. Great. We did it with a satellite that used to be a spy satellite that we repurposed. So rather than NASA spending $1 billion+ to design a new satellite, get it into orbit and hope it works, they had one already up there. So yeah, I think it's a great way for US taxpayers to save billions of dollars in order for professional radio astronomers to get radio telescopes in orbit quickly.
So you would be surprised if they were already doing this.
It wouldn't surprise me at all if they were already doing it, because if they repurpose a clandestine satellite, it may only be a small number of people that are allowed to know they're even doing it. It has to be a no longer classified spy satellite. So it's got to be real obsolete technology, which for my purposes would be fine.
So you're thinking that they could already be doing this, and that what you would be liking to do is say, oh, so you have someone doing this. Can I get in touch with them so they could send me some pictures?
Not for the pictures. I would just like the confirmation that we've officially, with confirmation, detected a black dwarf star. If we receive the radio signals from it and know that it's there, they can then go multispectral and task the James Webb Space Telescope, the Hubble Space Telescope, to go look at them and see if they can see any planets around them.
But right now we don't have anybody coming out and saying that they can do that.
That is correct. Nobody's out there saying it, but I think it's a possibility, and I would like to have them tell me it's not a possibility.
Oh, you want them to tell you it is a possibility.
I would like for them to, but if it's currently a clandestine satellite, they're just going to say, thank you for your comments. And they did that, which to me would say, oh, they may already be doing it, or, oh, they don't have any of their satellites that are declassified. They may have shut them down. They may have put them in an orbit above geosynchronous over Hawaii just to like park them, but they're still classified technology. But what would be the harm? The harm would be if the technology of the spy satellite is too new, then it would tell our enemies what we're capable of. So if all of a sudden we said, we've repurposed a former spy satellite that's been declassified, it has a football field diameter radio antenna on it, but it's a mesh, so the sunlight passes through it, so we don't see it as highly reflective. Because it's in radio, you can do that. If it's in a certain frequency of radio, the dish has to be solid, but it'll be smaller. It'll open up like an umbrella. But if it's a giant radio antenna because you want to pick up some guy's cell phone in a cave somewhere, that's going to be an enormous antenna, but it can be a slightly more open mesh, so we can't see it from Earth. But if all of a sudden the US said, we have a new radio astronomy telescope, it's a repurposed signals intelligence satellite, and it's got a football field size antenna. We didn't recently launch that thing. Somebody's going to go look up its satellite ID, and even the spy satellites have a NORAD identifier, or what is internationally known as a COSPAR ID. You can look them up on heavens-above.com and say, what's that satellite? And if it just says classified, you know it's a spy satellite. You have no information about it. But if it's not a spy satellite, then you can look up all the gory details on it. So I'm hoping they have something up there that can contribute to professional radio astronomy.
Sounds good. I hope they watch this.
Well, I'm going to try and get it out tomorrow. Okay,
Okay.
we're going to stop recording now.